Hello and welcome to Pep Talk with me, Mr. Pepperell. In this episode we're thinking about the penetrating power of nuclear radiation. By the end of this video you should be able to tell me how far each type of radiation can actually travel in there and what can actually stop it.
So these are the radioactive sources that we use in school, that we use for experiments and demonstrations and stuff, and we keep them inside this big heavy lead block. Now why, you might ask, why do we have to keep them inside a lead block? Because of their penetrating power. So I know that different types of radiation have different penetrating powers, but to work out which one is the most powerful or can penetrate the furthest, I'm going to have to set up an experiment. So what I'm going to do is set up my radioactive source pointing towards my Geiger counter over here so that my counter can begin to take readings of the radioactive emissions. And obviously on my counter I've got a little number here which starts to go up when I start to detect the radiation. Now really what I should have done here is taken into account the count caused by the background radiation that we talked about before. But as I'm not carrying out a quantitative investigation, I'm not actually interested in the actual numbers of my count, I'm just comparing my sources. I'm not too worried about the background radiation for now. Now, to measure my radiation's range in the air, all I need to do is start to slowly move my radioactive source away from my counter, okay, and I just need to keep moving it away until my clicks stop. And when my clicks stop, that shows me that my source is too far away, that the radiation is not penetrating the air, and then all I do is measure the distance between my source and my counter to work out the range in air. Okay, if the radiation is penetrating the air, I'm obviously still going to be getting a count on my counter. When I take it too far away, I'm not going to be getting a count. I need to measure the distance at which my counter stops detecting the radiation. Now, to determine which materials are absorbing my radiation, all I need to do is place my material in the way of my radioactive emission. If it doesn't affect my count rate, then my material is not absorbing the radiation. Then what I need to do is select a different material, place that in front of my radioactive emissions. If my counter stops counting, if my count rate drops, that means that I've got an absorbing material.
Okay, so let's have a look at our different radiation sources and investigate their penetrating power in the air and see what sort of materials are going to absorb them. I've got them here in my block that we saw before, and first up is our alpha source. Okay, it's on the end of this sort of plastic pen here to make sure I'm not touching it because obviously it's a radioactive material. Okay, but in the end up here we've got the source, the alpha emitter. Okay, now if we have a look over here, this is our Geiger counter, and you can just about make out those numbers there. Okay, we can see that the background radiation is being picked up by the actual counter, the actual tube, which is just here. And each time this number ticks up, that means another particle's been detected. So firstly, let's see how well the alpha particles can penetrate through the air. Okay, so if I place the alpha source right down close to the detector, we can see there that those numbers are starting to go up really, really fast. Okay, it's going 90, 100, 110, 120. But as I start to bring that away, we can see really quickly that the numbers have stopped going up quite as fast, and now they're just going up at the same speed they would have done with the background radiation. Okay, so we can see the penetrating power of alpha radiation in air, not very good at all. It won't penetrate very far at all. Let's see what sort of materials it can actually penetrate through. So I'm just going to insert my alpha source into the holder there, so I don't have to be holding on to it. I'm going to spin it round over the top of the Geiger Müller tube and just lower it down so I can see that it's set in there. Okay, so I can just about see that. My if I get it lined up nicely. There you go, my count is just starting to go up, so it's going through that amount of air, okay? But if I just get a normal piece of paper like this, and I stick the piece of paper in the way, we can see that the count has slowed right down and has practically stopped, okay? So, alpha won't penetrate through very much air, and it's pretty much just stopped by a piece of paper. So, I've reset the Geiger counter. We're back to, well, it's now ticking up again because of the background radiation. But now we're going to have a look at the beta source, okay? Stored in the lead block again to make sure that the user is protected on the end of the plastic thing so I can keep it at arm's length. Okay, let's have a little look at the penetrating power of our beta source. So I can just show you on there. Look, we've got a little beta sign on there. This is our beta source. Can it penetrate the air? Well, keep an eye on the Geiger counter down here. When I put it close, straight away we can see those numbers are flying up, 1,000, 1,500, 2,000. And as I start to take it away, look, that count rate is not really going down very much. If I take it a bit further away, not really going down, okay? But as I start to get a little bit further away, obviously my aim's not very good, but as I start to get further away, you'll start to see that count rate is slowing down, okay? Because really we expect that a beta source will be able to penetrate through about 30 centimetres of air, okay? So more penetrating than the alpha one that we saw just now. But what about penetrating through different materials? So I'm going to insert it into the holder here so that I'm not putting myself at risk. Safety first. Let's bring it over so we make sure that we're actually detecting it again. So we can see, I'll tell you what, I'll reset that back to 0. So we can see those numbers flying up again now, okay? What about our piece of paper that we used just now for the alpha source? If we stick that in there, you wouldn't even know it was there. No real change to the count rate at all. But if we just get a little thin piece of aluminium like this, and I stick the piece of aluminium between the two, boom, stops straight away. Okay, so beta penetrates through about 30 centimetres of air, penetrates through paper, but a piece of aluminium like that is enough to stop a beta particle. So, last but not least, we're on to our third source, and this time it is our gamma source. Now, you might be able to see from here, oh God, that's heavy. If I lift this up, the gamma source is kept right in the middle of this really heavy, thick lead block. That should give you a bit of a clue, really, about the penetrating power, but let's have a little look for it. Okay, so, let's put it, I'll be safe with this one. So, firstly, back to 0 there, you can be able to see that on there. I've got my gamma source out here. Let's just turn this out of the way a second. My gamma source, I'm bringing over, and over the top there, we can see that count rate is starting to go up now, okay? But as I bring it further away, okay, if I keep my aim right, pointing in the right direction, it's the trouble with trying to, aim it down a little hole. The count rate's not really changing there. It's going up still. It's not really changing. Any change there is probably due to me like doing this and missing the Geiger Müller tube, to be honest. Okay, so the gamma is not going to be affected by the air at all. It's going to keep on penetrating. It's going to go through the air there. So our alpha stopped by a couple of centimetres of air. Beta, 30 centimetres of air. Gamma, unaffected by that, okay? But what about its penetrating power looking at different materials? So let's just bring it over the top here. So I've got that in position now. We can see that count rate's going up quite nicely now, actually. So our materials, our piece of paper again, let's just slot that in there. Might as well not be there. Count rate's still going up the same amount. Our piece of aluminium that we used before, exactly the same piece. Let's just put that in. Nothing really, nothing that I can notice. Count rate's not really changed. What about, this is lead now, dense, really dense material. Let's have a little check with the lead. Let's put that in there. Well, to my eye, it might have slowed down a little bit, but not that much. Let's have another look here. Now we've got a really, that's a thick layer of lead. There's probably, 10 or 11 millimetres of lead there. Let's put that in the way and see if we've got any effect. Well, now the count rate has slowed right down. Okay, we can see it's still ticking up though, but it has slowed right down. So we can see that it takes a really thick layer of a very dense material like lead to stop gamma radiation. That's going to penetrate through paper, aluminium, your clothes, your skin. Okay, so gamma is the most penetrating of all the radiations we're looking at, all three ionising radiations, and that's why when we store it right in that middle hole there of our lead block to make sure that the teachers and the technicians particularly are protected when we're using that in experiments or demonstrations in school. So that's a lot of information. Let's just summarise that now, and I think it might be a good idea for you perhaps to use a little table, just sketch one out a little bit like this, for you to record the type of radiation, the absorbent materials and the range in air. So just pause this, sketch yourself a table in your notes, or make your notes however is best for you. As we saw, alpha was the least penetrating of the radiations we looked at. It only had a range of about 50 millimetres or 5 centimetres in air, and it only took something as thin as a piece of paper to stop it. It was absorbed by the paper, so alpha was our least penetrating type of radiation. Next up was beta, which had a range of around 1 metre in the air, but it was blocked by my aluminium. Okay, so that was my next penetrating type of radiation, range of a metre in air. It was blocked by my aluminium or a thin piece of lead. Okay, and finally we had our gamma source, which had practically an unlimited range in the air. Okay, although the energy is actually spread out the further you get from the source, so it doesn't sort of go on forever. The energy does get spread out. But it did take a thick piece of lead to absorb the gamma, or in practicalities it would take almost a metre of concrete to absorb the gamma. Okay, and that's why we actually stored our gamma source in school that we saw at the start in the middle of that lead block, because it is the most penetrating and it takes a thick layer of lead to stop it. So that's everything we need to know about the penetrating power of nuclear radiation. Any problems with that, don't hesitate to tweet me at Mr_Pepperell or email me and I'll get back to you ASAP. Thanks for stopping by.